Okay, so I just wanted to start with a real quick example illustrating the use of the open system energy balance. And then we're going to kind of continue to delve through chapter 3. I'm going to review the equations for isothermal compression / expansion, and also the adiabatic expansion path, because that's one of the most important ones. And then hopefully we'll have enough time to finish with a quick example on how to use the cubic equations of state, which is the topic of the equation sheet handout for today. There is a second homework set. I've got one copy left up here and another couple copies of the equation sheet handout if you don't have one. Okay, so we finished a few days ago, and it seems like forever ago now, reminding you all of what the open system energy balance looked like and identifying some of the terms. So there they are again. So let's look at a quick system that uses those. So we're going to consider an example that features liquid methanol. Are you familiar with that notation for methanol? So Me is a frequent OChem shorthand for methyl, and OH is obviously methanol. So you'll see et OH for ethanol, et cetera, a lot of times. Okay, so we have liquid methanol at 10 degrees C, and we're going to pump it up a large vertical distance, and we're going to pass it through a heat exchanger. So let's so you have MEOH at 10 degrees C, and that's going to go through a pump. There's going to be some work injected into the system through the action of the pump. We are going to pass it through a heat exchanger, and then it's going to go up a certain height to its final location. All right, the flow rate that's going to be 10 moles per second. And if we look at, is this all big enough for folks to read? Can you see stuff? Good. Flow rate is 10 moles per second. The amount of work the pump is injecting into the fluid is 10 horsepower. Hooray, horsepower units. And the heat exchanger is doing a good old SI, nearly SI, 10 kilojoules per second. All right, so let's start with the energy balance and start crossing some stuff off. The process, we're going to assume to be steady state. All right, so first of all, what do you want to take as the system for this process? Where should I draw my, and I guess the final question is, what's the final temperature of the methanol? So how do I find the final temperature of the methanol? I'm going to do an energy balance. First step, the energy balance, I need to find the system. So where do you think I should draw my system boundaries? Probably one right here. And if I want to account for all the features, then I should probably draw the exit of the system after all those different features have had a chance to take effect. Oh, my delta Z is 10 meters. All right, so we'll start with the whole thing. So I'm going to have my internal energy term. I'm going to have a big delta term, and that is going to have an m dot h in it. We're going to have an m dot over 2 u squared and an m dot zg equal to the rate of heat input plus the rate of work input. Okay, so this part right there, keep or discard? Why? Steady state. All right, that's the easy one. Actually, a lot of these are pretty easy. All right, so that's steady state. That's why that goes away. All right, I've written the delta term with the m dots on the inside of the brackets. So most of the time the m dots can come outside. How do I tell? When can I factor it out? When do I have to leave it inside? If m dot is the same on the inlet side and the outlet side, then it's a constant as far as this delta is concerned. And anything that's a constant factor in here can be factored outside of the delta. So in this case, the m dot can come out if I want it to. So the h, this is going to contain the temperature information in it that I need to answer the problem. So that one's obviously going to stay. How about kinetic energy here? Do you think kinetic energy is important in this one? Yeah, the flow rate's constant. We're not given any weird information about changes in pipe diameters. Most of the time, the kinetic energy is negligible. You did a problem in the homework where you looked at a case where you had some pretty large changes in pipe diameters, and you saw, hopefully, that the temperature changes associated with that were really small. So most of the time, this is going to be a no-go, and you'll cross that out to 0. Incidentally, if I were going to keep the kinetic energy term, which way is correct, 1 or 2? So 1, it's m dot over 2 u2 squared minus u1 squared. And method 2, m dot over 2 u2 minus u1 squared. Number 1, that is correct. Oops. All right, that is a minor point of confusion I see people have sometimes. All right, the MZG term, the problem gave us a fairly large delta Z, so probably part of the point of the problem is to see if it matters or not, so we're going to keep it. And then we are given some information about Q and W. All right, so let's go through the the information we're given and then transform it into the form that we need to plug it into the equation. So we are given an n dot, and the equation is written in terms of m dot, and so we can translate it, the whole equation, over to molar, or we can translate the whole thing to a mass base. So let's do so our m dot methanol is going to be the n dot methanol times the mass per mole. And so that was 10 moles per second. And then let's see, for water, that's 32 grams per mole. So, no, this is methanol, sorry. So 32 kilograms methanol per mole. And so that is going to give us 0.32 kilograms per second. The work term is given to us in horsepower. And to convert from horsepower, if you don't have that factor in the top of your head, you're going to remember Appendix A in the textbook. All right, so 1 kilowatt is 1.34 horsepower. And so that is going to work out to be 7.48 kilojoules per second. All right, the heat term is already given for us in a convenient format. And so we just need the MZG term. So that's going to be 0.32 kilograms per second times 10 meters times 9.81 meters per second squared. And that works out to be 0.0314 kilojoules per second. So it's not huge, not in any way, shape, or form, especially if you compare to the 10 kilojoules per second the heat exchanger is applying and the 10 horsepower that the pump is applying. So you would probably be okay neglecting that, and we're not going to get a huge difference in this case by including it. All right, so we are going to have our final energy balance here is going to be 0.32 kilograms per second times delta H, plus 0 for the kinetic energy term, plus 0.314 kilojoules per second for the potential energy term, and that's 10 kilowatts for the Q dot, plus 7.48 kilowatts for the W dot. Yeah.
For the MG term, what did you get 0.0314 from those Is it like, did you just like convert units at some point?
Yeah, so this is kilograms meter squared per second squared is
Right.
going to give me SI, so that's
Right.
joules. So that should be 3.2 and then 31.4. And then we're going to slide it over 3 points for kilojoules. Yeah.
You said we could neglect that value. What if we were looking at a problem where we were looking at the lifetime? So that long, so like for a year or something, that would add up to quite a bit.
Well, it depends what I want the information for, right? So if you compare the energy the pump is applying to the energy that it actually takes to push the fluid up the pipe, you see there's a big mismatch there. So there's obviously something else going on if the pump is generating that much power. Just from the point of view of I want to know what the temperature change is. I look at all the different terms that were given to me in the energy balance. This one is really small compared to these two. So we're talking a couple orders of magnitude less. So neglecting this is going to be less than a 1% error. So when you put it all together, we're going to get delta H is 54.5 kilojoules per kilogram. So that's just summing the right-hand side to the 17.5. It's not going to change much when I subtract off the potential energy term. And then I'm going to multiply it roughly by 3 when I divide by 0.32. So 17.5 times 3 gets me to roughly this point. And so that's what I actually get when I run it through with a calculator. All right, so now that I got to a delta H, we know that delta H is equal to, and this is, is just going to be the familiar heat capacity integral. So for ideal gases and for liquids, it's basically a function of temperature only, unless you're talking about really, really ridiculous pressure changes. Liquids are nearly incompressible. So then at this point, I can just go into the back of the text and look for the CP over R value for methanol. And see, I have that written down somewhere. That is 13.4 minus 51.28 times 10 to the minus 3. Plus 131 times 10 to the minus 6 T squared. So that's going to be 13.4 T2 minus T1 plus 51.28 over 2 e to the minus 3 T2 squared minus T1 squared plus 131 times 10 to the minus 6 over 3 T2 cubed minus T1 cubed. Okay, what are some, and at this point I got one equation and one unknown. I know delta H, I know T1, so I just have to solve for T2. So what are some of your favorite ways of doing that? How did you do it for the homework? You've had to do it for the homework. Yeah, you could graph it. That's an acceptable way of doing it. You're not going to get the world's greatest accuracy for graphing, but for some applications, that's going to be good enough. How many of you have a calculator that's more powerful than what you'd find at the grocery store? A lot of graphing calculators. Those have an equation solve function in them, right? That's a very good tool to know how to use if you have one of those calculators. How many of you did it with a spreadsheet? No? Familiar with the goal seek tool? So you could basically enter this formula in one cell where T2 is an unknown cell, and you put a guess in that cell for T2, and then in your expression cell, you would have the entire expression that uses your guess value for T2. And then you tell goal seek to adjust your unknown cell until your expression cell has a value of 54.5, because you know that's what it has to evaluate to. So that is a quick and easy way to do it. But since most of you are doing your homework, it tables the calculator out. The solver utility on your calculator is a great way to do that. All right, any questions on this example? It's pretty straightforward. All right, so next topic, we want to go back to our cylinder example where we had state 1, we had state 4, we were at 0.61 liters and 298 K. We were at 2.44 liters and 298 K. And we were looking at the various ways of doing that. And so last week we spent quite a bit of time looking at isobaric and isochoric paths. And now I want to quickly review a couple other common paths that you take when we're doing state change calculations. So let's sketch. So if I take a path that looks like that, and the equation of the curve that I used to draw that was RT over P. It's basically what an isothermal compression pathway looks like. So if T is left constant, then that's basically the shape that you're going to get. All right, so all of these equations that you've seen in 210 and you've seen in Chem 325 for these various expansion paths all derive directly from the first law. And so remember, the first law was UT equals Q plus W. And in differential form, DUT equals DQ plus DW. And we already rationalized why the dW term was was minus PDV. And we also know that DUT is NCVDT. So if you remember the beginning of this derivation that we see a bunch of times, it'll be easier to remember how we get to these other equations. And the whole idea here is we want the differentials expressed in terms of the independent variables that we know how to manipulate. So that's going to be T, V, and P for single component systems are basically the three independent variables that we're playing with. Sometimes we want to be able to use P and V, some other times T and V, other times T and P. And the way that you switch in between variables is by being able to work through these equations. So if you put dq all over on one side by itself, and we can drop the n for now, because we're going to just assume we have a constant mole system. So that's the intensive form. This is kind of the starting point for a lot of these various equations that we're using to calculate heat and work in these state change problems. All right, so if the compression is isothermal, what that means physically is I take my cylinder, I'm going to put into a constant temperature bath, and then I'm very slowly going to compress the fluid, allowing any heat or any temperature change that is generated in the gas as I compress it to be transferred out into the water bath. Okay, so that means the temperature change is 0. So for an isothermal process, at dT, I can cross out. All right, one thing I need to point out here is when we're doing all these manipulations, what's implicit, especially when I'm working in differential form, is that the macroscopic process that I'm modeling it as an ideal process. So in a real process, if I was trying to mimic an isothermal compression, I put my cylinder in the ice bath or the water bath or whatever, and I'm not going to be able to push the cylinder down infinitesimally slowly. So what that means is that the temperature, the gas inside the cylinder is going to raise temperature. It is going to start as roughly adiabatic actually over a short period of time. The temperature is going to rise, and then you're going to have a temperature gradient between the interior of the cylinder and the bath, and then that temperature gradient is going to allow heat to flow out of the gas into the surroundings, returning the temperature back to roughly that constant state. So that's like an isothermal process, but it's not an isothermal process. So this isothermal process is completely in our heads. And so again, the reason why we bother in the first place is we can actually work out the math for these simplified processes, so we can actually get somewhere. And then B, all is not lost. Real processes are approximations of ideal processes. So if we're able to introduce efficiency factors, those sorts of things that we can either derive using more sophisticated modeling techniques or measure directly just by doing experiments, then the effort was worthwhile in constructing the artificial ideal system. So anyways, for an ideal reversible isothermal process, we just get down to the differential amount of heat is equal to PDV. Remember, that's minus dW. So the Q for an isothermal process is just the integral from V1 to V2 of PDV. And then here is where we get to an application of the ideal gas law again. So if it's an ideal gas, then that's RT over VdV. If it's an isothermal process, both the R and the T are constant. And so I'm just left with dV over V and the integral of 1 over V, of course, is the natural log. And so that's how we get to Q equals minus W equals RT natural log V2 over V1. And again, you can use ideal gas law to transform that into pressure coordinates if you prefer. It's all the same thing. Yes? So I'm making an ideal gas constraint here. Now, if you review these derivations in the book, they're actually in a section where it says relationships for ideal gases. You still with me? Yeah? Yes?
And the integrals, are those U's or V's?
Those are V's. Okay, so if I wanted to calculate Q and W for this isothermal process, then it's pretty straightforward now, especially if I'm assuming that I have an ideal gas. Okay, another way of going from point 1 to point 4. Again, we'll have PV, we'll have point 1. I'm going to draw point 4 a little bit lower this time. So this time, I'm going to compress the gas. I'm going to use a very well-insulated cylinder this time. So there's absolutely no heat transfer allowed through the cylinder walls or the piston or the floor of the cylinder. So you've probably experienced this effect when you're pumping up a bike tire or something. You'll feel the hose get hot. You'll feel the tire get hot. You've experienced the reverse of this effect if you've ever used an air duster and spray in compressed air for a while, and then all of a sudden the can gets too cold to hold comfortably, or sometimes you can even get condensed liquid coming out of the spray nozzle. Hopefully you've all had those experiences. So that's kind of like an adiabatic process. So you can feel the tire getting hot or the can getting cold. All right, is nobody ever played with the air duster? Yes? I will bring air duster to class and we can play with it if you haven't had this simple experience. I got 3 cans of it at home. We can have an air duster party. And you thought chemical engineers didn't have any fun. Anyway, so that is kind of like an adiabatic process. It's obviously not, because you can feel the hot or the cold. However, you're applying the compression and the expansion more quickly than the heat is able to dissipate. If you're doing it slowly, then your tire would always be at equilibrium thermally with the air in your garage or whatever, and it would be an isothermal process. So the rate at which you do something matters, in which process it mimics changes depending on those sorts of things. But at any rate, so if we compress the cylinder really quickly, too quickly for any heat to escape, then it's going to be another curve. And it's usually not going to be a great equation to describe the path of that curve. We'll get to an exception to that. So if I don't do anything to release the heat, then I'm going to end up injecting all that mechanical energy and converting it all into stored thermal energy by raising the temperature. And so then if I wanted to get to 0.4, then I would have to do an isochoric cooling step in order to drop the pressure back down to the 40 atmospheres. So what this is saying is if I do adiabatic compression and I go from my 2.44 liters to my final 0.61 liters, I'm going to end up having to over-pressurize in order to get it to that final volume. And then to get to the final pressure, I'm going to have to cool it down a little bit. Okay, so I don't have to start completely from scratch. So to figure this one out, we'll start with the differential form of the first law solved for dq. So dq is CV dt plus PdV. Yes?
But how come we can't just go from 1 to 4? Like, or-
That's isothermal. So if I want to go directly from 1 to 4 and have the initial and final temperature be the same, then the ice bath way, or I guess the water bath way, is how I want to do that. So if I do it too fast, even if I have a water bath, that heat isn't going to have time to escape, and so it's going to overshoot temperature-wise. And if I do it quickly enough or I'm well insulated enough, it's going to approximate a perfectly adiabatic system. So if it's an adiabatic system, that means that the dq is the term that cancels out. And then I'm left with the right side, which is expressed in terms of temperature and volume. And I can use that directly if I want. So then I'll have 0 equals CV dt plus PdV. And what that means, by the way, is remember the CV dt is the delta U part, and PdV is minus W. So for an adiabatic process, 0 equals delta U minus W. And so what that says is that all the mechanical energy that you inject into the system doing the compression is converted into internal energy. And so 100% of that energy is stored. And that's kind of an ideal assumption, right? So you're assuming that all of the effort you put into a process is being stored, that you can extract it back later. And that's obviously not going to be the case in the real world. All right, so if we want to do some calculations with this, one thing that we could do is make an ideal gas law constraint. And so then I'll have minus CV dt on the left-hand side. And then on the right-hand side, I can write RT over V dV. Now this time, the temperature, I'm not allowed to pretend that's constant. So what I can do, though, is I can sort out the two different variables. So this is expressed in temperature and volume. So if I get the temperatures all by themselves on one side, then on the right-hand side, I'm going to have dV over V again. Oops, dV over V. Now here I'm at a point where I can integrate, and if depending on what further assumptions or constraints that I apply, it's going to be an easier problem or a harder problem. So a lot of the equations you may have seen before for adiabatic expansion is you're going to neglect the temperature dependence of the heat capacity, which can be okay or it can be really not okay. And we'll kind of illustrate that here in a minute. But at any rate, if you neglect the temperature dependence of the heat capacity, then you're free to integrate both sides, treating the CV over R as a constant. At this point, most texts like to define a new parameter. And by the way, when I did ideal gas constraint, those are ideal gas heat capacities. And ideal gas heat capacities are convenient because they are only functions of temperature. So they're not ever a function of V or P. They usually are functions of temperature, and sometimes you can get away with pretending that they're not. So at any rate, gamma is just simply going to be the ratio of CP to CV. And if you play around with that definition, as well as the fact that, remember, CPIG equals CVIG plus R, we get to substitutions such as the following. So CVIG is the same as R over gamma minus 1, and CPIG is the same as R times gamma over gamma minus 1. And so the gammas are what you see published in the textbook for a lot of these adiabatic expansion problems. So at any rate, if I go ahead and use that substitution in this equation, then I am going to get 1 over 1 minus gamma. And so to account for the negative sign, I just switch the ordering of the terms in the denominator there. dt over t equals dv over v. And so if the heat capacities are not functions of temperature, then that means gamma is also not a function of temperature. So that means that the natural log of T2, T1 times 1 over 1 minus gamma. I accounted for that by swapping the order of the denominator. So I've got 1 minus gamma here and gamma minus 1 there. I could write it like that, and it would have the negative sign. So then again, if I integrate both sides, I'm going to have a 1 over 1 minus gamma factor multiplying the logarithm of the ratio of the temperatures on one side and the logarithm of the ratios of the volumes on the other side. And it is that derivation where equations such as this come from. And so these are just pulled straight out of the book. But remember, these equations are only valid for ideal gas. And CV is not a function of temperature. Okay, if these constraints get in your way and you're not able to do what you need to do, you go far enough back up in the derivation until you've got something you can work with. So way up here, we don't have ideal gas and we don't have constant temperature or anything. Down here, if we can live with ideal gas, but not constant temperature heat capacity, we've got a form that's actually pretty easy to work with as well. And next time I'll illustrate how we do it with temperature dependence included. I think this time I'm just going to show you a really quick example of what happens if you don't include the temperature dependence. So we're looking at this example still. So we're going from V1 equals 2.44 liters to V2 equals 0.61 liters. P1 was 10 atmospheres. We don't know P2. T1 is 298 degrees Kelvin. And we also don't know T2 yet. That'll be the first thing that we calculate actually using the adiabatic compression relationship. Okay, so if I want to use this equation, I'm going to need a value for gamma. And our working fluid here was methane again. And our CpIg over R was 1.7 plus 9.1 times 10 to the minus 3 T minus 2.2 times 10 to the minus 6 T squared. So at a temperature of 298, so gamma of 298 Kelvin is equal to CpIg over R at 298 over CpIg over R evaluated at 298 minus 1. You plug in the numbers there and we are going to get a value for gamma equal to 1.31. So gamma 298 equals 1.31. All right, so now that's what the heat capacity ratio is at the beginning of the process. As I compress, the fluid is going to get hotter and the heat capacity is going to change. And the gamma value will be different at the end of the process. So what I'm going to do is I'm going to calculate, assuming that gamma is constant, what the endpoint temperature is. And then I'm going to calculate gamma again at the final temperature and see how much it's changed. And then Friday, we'll look at the consequences of that. So T2, using gamma 298, I'm going to calculate that just using this formula here. So that is going to be T1 times, V2 over V1 raised to the power of 1 over 1 minus gamma 298. All right, so I just moved this over here. Sorry. I just moved that over there and then exponentiated both sides. And sorry, that should be. I'm a minus 1 when I do that. I had to multiply both sides by gamma minus 1. All right, the temperature is going to be 458 Kelvin. And gamma evaluated, so the heat capacity ratio evaluated at 458 Kelvin comes out to 1.2 27. All right, so it's dropped by almost 10%. And so next time we'll see how much of a change that makes into what our final temperature is if we use a different gamma, and then we'll talk about some different ways to account for that changing value.